So good evening everyone. Today we are going to take the tutorial session on the week 10th of the course Introduction to Robotics. So basically in this course we will cover questions based on Kalman filter and extended Kalman filter. So what we will do, we will first start the basics of Kalman filter because and we'll explain like what is Kalman filter and what are the different parameters there in the Kalman filter. So before coming to the Kalman filter, first, we will see before solving any question something. So before solving the questions, we will see the basics of Kalman filter. I don't know why I'm able to join. So we will see the basics of Kalman filter before solving some questions. So base filter is one of the tool for the state estimation, what we have studied before. And Kalman filter is also a base filter only. So base filter is one of the tool for state estimation. And the student who is missing this lecture now can watch in the YouTube. The video link will be provided in the NPTEL tutorial session. So there is two steps here. One is the prediction and another is the correction. So the prediction step is given as belief bar of xt, that is equal to integration of probability of xt given that ut and the previous state xt minus 1 and belief of xt minus 1 d of xt minus 1, and the next step is the correction step. So that is given as eta, that is a scaling factor, probability of zt, that is measurement, given the current state xt into belief of xt bar. Okay. So here Kalman filter is a base filter. Just mention this, just remember this topic. Kalman filter is a base filter, and the optimal solution for it is also the optimal solution for linear models and Gaussian distribution, and it uses least square approach in this. Let's write this point. It is optimal solution for linear models and Gaussian distribution. Second, least square approach equivalent to Kalman filter in this case. So we have seen the prediction and correction step, what we have studied before. So now we will see about the basics of Kalman filter, which is based on the linear model. So it is based on the linear model. Like Kalman filter is solve the problem which is based on the linear model. If it is non-linear model, then extended Kalman filter and different variation of Kalman filter can be used. So any linear model can be represented as, let's suppose fx is a function that is ax plus b. So Kalman filter assumes a linear transition and observation model. Just note down this important point. Assumes a linear transition and observation model. So now we will write all the equation of Kalman filter. So the state xt can be given as the linear model as at into x of t minus 1 plus bt ut plus sigma t. Here at describes how the state evolved from t minus 1 to t without any noise. Okay. So at is a matrix that describes how the state. So this is some basic things I am teaching. So this will be helpful in understanding the Kalman filter. Evolves from t minus 1 to t without control or noise. Now BT is another matrix that describes how the control UT changes state from t minus 1 to t. So it describes how the control UT changes state from, like using the control UT, how the state is changing from t minus 1 to t. Now, this is the first equation. Second, for the measurement, ZT is equal to CTXT plus delta T. This is second equation. So here, CT is the matrix that describes how to map the state XT to an observation ZT. So CT describes how to map the state xt to an observation zt. And del t and epsilon t, here it is a noise, sorry, I have written sigma. So epsilon t and del t is independent and normally distributed with covariance rt and qt respectively. Okay, so it is independent and normally distributed noise with covariance RT and QT. Today we have very less question. That's why I am teaching some basics of this Kalman filter. And the student who is missing this lecture can watch this in YouTube as well. So now we will see the linear motion model and observation model using the Kalman filter. And after that, we will solve some questions based on this. Okay. So coming to the next part, that is linear motion model. So the noise here is Gaussian noise. So motion under the Gaussian noise leads to the probability xt such that the action ut and the state xt minus 1 is given. So motion under Gaussian noise leads to, so this is given as the magnitude of 2 pi RT. RT is the covariance of epsilon t to the power minus half. This is just a exponential of, we'll write in separate line. So this is equal to amount of 2 pi RT to the power of minus half exponential of minus half xt minus at xt minus 1 minus bt ut. So this at xt minus 1 plus bt ut came from here. So basically when we use the Gaussian random variable, then you know the formula, it comes e to the power of minus half mu minus xt. So this term came from the equation 1, and again it will be RT inverse covariance inverse, and it will become xt minus at x of t minus 1 minus btu. So RT is the noise of the motion here. So now coming to the linear observation model. So observation model depends upon the measurement step, that is using ZT. So here we will use equation 2. So probability of ZT such that the robot is in the state xt is given is equal to determinant of 2 pi qt exponential of minus half zt minus ct xt, and qt is the measurement noise here. And the prediction step, belief bar of xt can be given as integration of probability of xt such that ut comma xt minus 1 is given, the current action and the previous state is given, belief of x t minus 1 d of x t minus 1. And belief of xt. This equation just I have written. You can study this in more details in the probabilistic robotics book, chapter 3rd. So now we will see the algorithm of Kalman filter. and the equation of the Kalman filter algorithm. So the Kalman filter is a function of previous state, that is mu of t minus 1, comma covariance sigma of t minus 1, comma mu t and zt. So mu t bar is given as at. We have just replaced xt as mu t. At ut minus mu t minus 1 plus bt into ut. Ut is the action or control. The third equation is sigma bar t, that is equal to at sigma of t minus 1 at transpose plus rt. Fourth is Kalman gain, that is given as kt, that is equal to sigma bar of t. Maybe the notation in the lecture series was little different. I'm taking the standard notation which was given in this book. Now the mu t can be found as mu t bar plus kt, the measurement zt minus ct mu t bar, and sigma t is equal to I minus kt ct and sigma bar t. And the seventh step is just return the value of mu t comma sigma t. So this is the algorithm we can use. Now we'll solve some of the questions based on this. In extended Kalman filter, only changes was that two functions g and h were taken, that were just estimating the non-linear model to the linear model. So that can be used to solve the non-linear model motion also. That can be solved using extended Kalman filter. So now coming to the question first, which of the following algorithms make the Markov? So which of the following algorithms makes the Markov assumptions about the system dynamics? So in this, the Markov assumption is made by Kalman filter also, extended Kalman filter, particle filter, and binary based filter with static state. All of these algorithms use the Markov assumptions about the system dynamics. Coming to the question number 2, that is the Kalman filter update results in Gaussian belief state representation, and the Kalman filter assumes an exponential motion model. So the reason is wrong because the Kalman filter assumes an linear motion model. So the assertion is true because the Kalman filter assumes linear dynamics with Gaussian noise. So this assertion is true because it is true because the Kalman filter assumes linear dynamics with Gaussian noise. It is written correctly. So yes, I will write down this point. So the correct option is assertion is true, reason is false. So option C is the uh, correct one for this question. Now we'll move on to the next question, that is, assume that robot is moving in a circular trajectory. Which of the following are appropriate choices for state estimation? See, when a robot is moving in a circular trajectory, even if you move with constant velocity, this means the direction is changing. Sorry, constant speed. Direction changing and velocity is changing because velocity depends on the speed. So here we cannot use the Kalman filter. So this option is the wrong one. So it is non-linear trajectory. But what we can do, let's suppose, assume this robot is here at time stamp t. So we can take a tangent there and make it as a linear assumption. So that can be solved using the external extended Kalman filter, and also the particle filter can solve such kind of problems. So option B and C's are correct in this. Now moving on to the question number 4. So this is the question based on the Kalman filter algorithm, what we have studied before. So, so before solving this question, first let's write the Kalman filter algorithm. So Kalman filter algorithm is a function of mu t minus 1, sigma t minus 1, ut and zt. Just a small correction here. I have written mu t, it's ut. So the Kalman filter algorithm is the function of mu of t minus 1, covariance sigma t minus 1, ut, comma, zt. Okay. So the first step is mu t bar, that is equal to at mu t minus 1 plus bt ut. Okay. I guess here also I must have written the formula. Ut I have written correctly. Sigma bar t is equal to at sigma of t minus 1 at transpose plus rt. Kalman gain kt is given as plus qt inverse. And then mu t is given as mu bar t plus Kalman gain into observation zt minus ct mu bar t. And the covariance at t is given as identity matrix I minus kt ct into sigma bar t. And finally it returns mu t and covariance at time t. So now in this question, we will see what are given. So in this question, it is given that xt is equal to xt minus 1 plus ut plus epsilon. Okay. So we have also written the two equation that xt is equal to at xt minus 1 plus bt ut plus epsilon t. So here a is 1 and also bt is 1. Okay. Anyway, in this question, we A and B are 1 here. So we'll take this also into consideration. Here AT is equal to 1 and BT is also equal to 1. Here you can take I also because it's an identity matrix. It's not a one single variable, it's a matrix n cross m. And ZT is equal to XT plus eta. So I will just copy these two equation from here. Sorry. Let's copy this here. And the second equation, what we have used. So from here, we can see that our AT is 1, BT is 1, and CT is also 1. Now coming to the both eta and del. Here del T you can replace with as eta. So epsilon and eta are the zero mean Gaussian random variable with variance 0.1. Given that the initial belief is the Gaussian with zero mean and unit variance, U1 is 0.1, Z1 is 0.11, and initial belief is given as zero mean and unit variance. Okay. So which of the following is the closest to new belief state after a Kalman filter update? So now what we will do, we'll just simplify this equation according to the value above. So Kalman filter algorithm, here mu t minus 1, that is 0 because the initial belief is Gaussian with zero mean and unit variance. So our mu t minus 1 will be 0 and variance will be here 1. So this two parameter will be 0, 1. Ut is given as u1 is 0.1 and z1 is given as 0.11. So we can take 0.1 comma 0.11. Okay. So this is just our equivalent to mu of t minus 1 sigma of t minus 1 ut comma zt. Okay. So now mu t bar is equal to at, that is 1. So we'll ignore that. Mu t minus 1 plus mu t. So here we know that mu t minus 1 is 0. So this will become 0 plus mu t. So that is equal to 0.1. So this is equal to 0.1. Now the second is covariance T, covariance bar T, that is equal to sigma bar of T minus 1, A is 1 plus RT. So sigma of T minus 1 is 1 plus RT is the noise. So noise is given as with 0.1 variance. Here you can see are the Gaussian random variables, eta and epsilon is a zero mean Gaussian noise random variable with 0.1 as a variance. So here RT will be 0.1. So this is equal to 1.1. Now we have to find the Kalman gain KT. So KT is equal to sigma bar T. CT is again 1, so ignore that. And again sigma bar T, CT is 1 plus QT inverse. So this will become our sigma bar t is what we have find is 1.1 into sigma bar t is 1.1 plus qt is the covariance of the noise, so that is 0 0.1 inverse. So this will become 1.1 by 1.2. So this is equal to 11 by 12. So kt is equal to, when you simplify it, it will become 11 divided by 12. So this will become 0.917 or 666, something like that. Okay. Here you can write 666, whatever. So now the next step after finding the Kalman gain, mu t is equal to mu t bar plus kt zt minus mu t bar. So mu t bar what we have found 0.1 plus kt 0.917 into zt minus mu t bar. So what is our zt? That is 0.11. That is given minus 0.1. So this will become 0.1 plus 0.917, 0.01. So let's solve this using calculator only. 0.917 into 0.01. This is equal to this plus 0.1. So this will become 0.10917. So now we have found mu t also. So the last thing we have to find is covariance at t, that is equal to I minus kt sigma bar t. So I is 1. So that is equal to 1 minus Kalman gain k is 0.917 into, and sigma bar t is 1.1. So let's solve this. This is equal to 1 minus 0.917, 0.083 into 1.1. So this will become 0.0913. It was just a simple question we have taken. So finally, it returned this. So return mu t, that is 0.10917, comma sigma t, that is 0.0913. So we have just taken a simple question with one variable only, just to understand how we find the solution using the Kalman filter algorithm. We'll move on to the next question. So the importance weight used in a particle filter accounts for the observation probabilities. So weight is used in the particle filter for the observation probability. Yes, this is correct. And the importance weight used in particle filter accounts for the noise in the state transition model. So this is wrong. So the correct option for this question is option B. Because option B, so this statement 1 is true and statement 2 is false. So option B is the correct. Now moving to the next one, that is particle deprivation can be mitigated by which of the following? So the particle deprivation can be done by reinitializing the particles and also performing resampling less often. So option A and B are correct. So what are the challenges of particle filter? It have like finite number of particles, a representation can be biased, high variance and divergence, and particle deprivation. So the particle deprivation challenge can be solved using reinitializing the particles and performing resampling less often. So now we'll move on to the next set of questions. So that the first question is the Gaussian filters. The belief state is represented by multivariate normal function. So we have already studied. So it is just denoted like this. So this is a multivariate normal function Now we are coming to the question number 2. Which of the following is an application of the Kalman filter? So the Kalman filter is used for tracking system and also controlling the robots or estimating the motion of the robots or position of the robots. So here you can see human motion tracking. Yes, this is correct. Motion estimate of mobile robot. This is correct. Missile tracking also it's correct. We can track using Kalman filter and control of aerial robots. That is correct. We can control also using Kalman filter. So which is the primary goals of Kalman filter? Eliminate noise from sensor noise. No, this is not the goal. To minimize external influence on the system. No, Kalman filter cannot minimize the interference from the external on the system. Also to provide a smooth trajectory of the system response. No. To provide an accurate estimate of the system state. Yes, this is correct. Option D is the correct. So today we had very less question and a very simple question. So we will close the lecture here only. And if you have any doubt, you can watch this lecture in the YouTube, and also you can comment in the YouTube comment section. So thank you everyone for watching today's session. So we'll close the lecture here. Thank you.